Yesterday we learned about what it means to have a permutation versus a combination. With permutations, order matters, and with combinations, order does not matter. Today we are going to focus on some special cases. We are going to talk about what we do when we permutate items that are repeated. For example, if we have a word with two of the same letter, or if you are permutating the items within a circle. These are special cases and are dealt with slightly differently from linear permutations, where the items are chosen in a specific order and all of the items are unique. First of all, if we talked about how to arrange the letters in these words, if we looked at the word pig, we could come up with several options. For example, we could start with PIG, then we could do PGI, then we could start with the letter I and have IPG or IGP, and then lastly we could start with the letter G and have GIP or GPI. Now the way that we learned yesterday to arrange items is we said that we could do 3 letters in the first spot times 2 letters in the second spot times 1 letter in the third spot, or we could have 6 possible ways to arrange these letters. If we look at the options that we just got by hand, we also had 6 possible options. However, things start to get a little complicated when you have 2 of the same letter. For example, if you look at the word boo, if I tried to rearrange this, I would have B-O-O, but that looks the same as the B-O-O to begin with. There's no way to really denote that the first O and the second O are different. And the same thing is true with the word denim. Okay, so that leads us to think, how are we going to handle permutations that have repetition? What we're going to do, the general rule, is that we do n factorial divided by p factorial, q factorial, r factorial, etc. Now n stands for the total number of objects, and p, q, and r, etc. are the number of times an object repeats. So if we look at the word Mississippi, we can see first of all that we have 1, 2, 3, 4, 5, 6, 7, 8, 11 letters, so n would equal 11. And then we look at our repeats. The letter I appears 4 times, the letter S appears 4 times, and the letter P appears 2 times. So then to find the amount of permutations of the letters in the word Mississippi, including the fact that we have repeated objects that are really like the same object, we would do 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Now when you enter this in your calculator, it's important to make sure that you put parentheses around that denominator, so that way it multiplies all of those factorials together before dividing by 11 factorial. Now I put a note here on my notes that this is true not only for letters but also for objects that are the same. Other examples of when you might use this principle would be, for example, if you were permutating coins, like if you had a handful of pennies and nickels and dimes, you know, there's no real way to distinguish the 2 pennies. A penny is a penny, okay? So we would do this for coins. We would do this maybe if we had different flags that we were trying to arrange. You know, imagine you're having a garage sale and you've got these little triangular flags that you want to put up. You know, you might have some red, some white, some yellow. Well, they're all essentially the same flag. Or within words, having the same letters. Go ahead and try example 2 and 3. I have written the answers down here on the lower right of the screen. If we look at example 2 and 3, we'll see that on example 2, we are permutating the letters in the word attractive, and there are 2 A's and 3 T's. So the formula that we would use is 10 factorial divided by 2 factorial and 3 factorial. For number 3, we have 13 flags, and of those 13, 5 are red and 8 are white, and that is how we get this expression down here. Our next topic is circular permutations. A linear permutation is what we have been doing so far. We have items that are listed in a list, arranged in a row, etc. A circular permutation is when items are arranged in a circle. Now, examples of a circular permutation would be, for example, if I had people that were sitting at a table, If I had beads on a bracelet, or maybe I had keys on a key ring. These are all items that are on a circle, and the reason why we end up having less permutations is because there is no set starting point, and all of the combinations, all of the permutations that have the beads or the keys or the people at the table in the same arrangement are considered the same even if you have a different fixed reference point. Now that sounds kind of confusing. Let me show you what I mean by that. Let's say I had a table and I had 4 guests that were sitting at my table, and we will creatively call them A, B, C, and D. Alright, now if I were looking at a linear permutation, then the permutations A, B, C, D, B, C, D, A, C, D, A, B, and D, A, B, C, within a linear scenario, this gives me 4 different options. However, these 4 linear permutations match up with 1 circular arrangement at the table. These 4 people have not moved. This is 1 circular arrangement. And because of that, there are going to be n minus 1 factorial permutations, or I should say circular permutations, instead of the n factorial that we learned the other day. Now the way that we're going to go ahead and do this is we are going to treat one person or object as a fixed point and then permutate the other n minus 1 objects. And that is why we are doing n minus 1 factorial. So if you think about the scenario of the table that I have, I would pretty much say, all right, let's let person D stay put. Maybe that's the dad, maybe he doesn't ever get up, who knows. And then I'm going to take these kids, we'll call them kids, the A, B, and C, and arrange them. And I'm going to have them move around, and they're going to all sit in different places. And that would give me different circular permutations. Okay, let's go on to the next page and take a look at some examples. In the first example, I want to arrange 9 people at a table. This right here is your basic circular permutation. In a case like this, we would do 9 minus 1 factorial or 8 factorial. For the purpose of today's lesson, we're just going to leave all of our answers in factorials so that we can focus more on the setup of all the problems. Now in example 5, we are going to arrange 9 people at a table with 1 window seat. Now this is very important. This right here gives us a fixed reference point. Whenever we have a reference point, we are going to treat the circular permutation like a linear permutation. And in this case, we do the n factorial. And the reason why is because that reference point gives us a definitive starting point. The whole reason why with circular permutations we do n minus 1 is because there's no set starting point. However, if we have a specific seat, sitting by the window, or the head of the table, or a special bead on your bracelet, that gives a fixed point of reference and no longer is it considered circular. In that case, we're going to do n factorial. So here, when we have 9 people at a table with only 1 window seat, we would do 9 factorial. Now another idea that we're going to talk about is what's called the reflection principle. And sometimes our circular permutation has a line of reflection. Essentially, you could flip the object over in your hand and view it the other way. if you can do this, then you need to divide the number of permutations by 2 because you have essentially repeated the same permutation. So in this case, you are going to divide the number of permutations by 2. So we would either use n minus 1 factorial over 2 or n factorial over 2, depending upon if we had a fixed reference point or no reference point. So let's talk about keywords that we want to read for as we're looking through this. In number 6, we see that we have 6 beads on a bracelet. First of all, no mention of a specific reference point. Therefore, we are going to do the n minus 1 factorial. However, a bracelet, you can easily turn that over in your hand. So we need to divide by 2, giving us 5 factorial divided by 2, which if we were to solve that would give me 60. If we look at number 7, the difference here is that now we are doing 6 beads on a bracelet with a clasp. So the fact that we have 6 beads on a bracelet, it can easily be turned over in our hands, and the clasp means that we have a fixed reference point. So instead of doing n minus 1, we do n factorial, and then we divide by 2 because it could easily be flipped over in our hand. So we would have 6 factorial divided by 2, which gives us 360 options. Alright, now these last 2 are examples of how we could algebraically go ahead and solve problems with permutations. We learned yesterday that when we are given a permutation, either of the form Pn, R or NPR, in either one of these cases, we can set up an expression that says n factorial over n minus r quantity factorial. And we're going to use that idea to go ahead and solve both of these expressions. In example 8, I'm going to go ahead and set this up, and I'm going to say that n is my n and 2 is my r. Therefore, I have n factorial divided by n minus 2 factorial is equal to 56. Now, we talked the other day about always setting the larger factorial and rewriting it in terms of the smaller one. If we compare n and n minus 2, n is clearly the larger factorial. So we could rewrite this as n times n minus 1 times n minus 2, woohoo, we got a match, put an exclamation point, over n minus 2 factorial equal to 56. From here, we can see the n minus 2 factorials cancel, and we are left with n times n minus 1 equaling to 56. And this gives us a basic quadratic that we can go ahead and solve, getting n minus 8, n plus 7. Values of n would equal 8 and negative 7. Now, since the values of n represent how many terms we are permutating, you cannot permutate a negative number of terms. And for that reason, the only answer here is 8. Go ahead and try number 9. The answer for number 9 is 12. In this problem, rather than going ahead and writing n factorial in terms of n minus 6 factorial, I decided to go ahead and cross multiply. After cross multiplying, I end up getting the expression that you see down here in red. This expression is much easier to work with. I can cross off the n factorials, and then I can rewrite my other one. I can rewrite this such that I have the bigger one. Now, if you think about it, which one's bigger, n minus 4, n minus 6? n minus 4 is bigger because n minus 6 has taken away more from n. So I would have n minus 4, n minus 5, n minus 6, throw on a factorial, over n minus 6 factorial equals 56. These would cross off, and then I have n squared minus 9n plus 20 equals 56. If we finish solving, we end up getting the only answer that works is n equals 12. Thanks, have a great day.